So here we're going to be looking at the profit maximizing quantity for a monopolist, numerical example of that. And this is from my textbook in microeconomics, and I'm Rickard Friberg. Okay, so we're thinking of a firm that's the only one producing a good on the market as a monopoly. To be specific, we're assuming that it has a particular inverse demand function. So there's an intercept prices. I think there's a price of the good that it's getting. It's an intercept, and then the more it's producing, the lower is the price that people are willing to pay for units on the margin. Okay. There's associated cost. Nothing in life is free. So cost of producing Q units is given by a fixed cost, free, plus Q star, the variable cost, or a Q star, Q square, sorry. Okay, so given this, how much should the firm produce? What should the profit maximizing quantity be? Well, we're using some calculus here. So we're saying the firm wants to maximize prices, maximize profits. So it's choosing quantity to maximize profits. What are profits? Well, it's price times quantity. What's price? Well, in this case, we know that price depends on quantity. So 12 minus Q, that's P of Q, that's price, times the quantity. So this is revenue, minus the cost, 3 plus Q square. So we want to choose, the firm maximizes profits, want to choose quantity so as to maximize this expression. Okay, we can expand a bit here, multiply in and take away the parenthesis to be extra clear. Say that this is the same equivalent to maximizing 12Q minus Q star minus 3 minus Q star. Okay. So this is a profit. We want to find the top of the hill. We differentiate profit function with respect to quantity and set the slope, the tangent, equal to 0. That means that we've found that's a sufficient condition for having found an optimum profit maximizing quantity. Okay. Well, not sufficient, sorry, necessary. And will be sufficient in the case that we're looking at. So 12Q, differentiate with respect to Q, that's 12. 2 moves down here, minus 2Q, 3 drops, and then minus 2Q. And we said this should be equal to 0 at the optimum, okay? What do we have here? We have the marginal revenue, and this, the marginal cost. Okay, so let's draw this to help with the intuition. Like this. So we have quantity on the horizontal axis, price on the vertical. So let's illustrate. We have the demand curve like this. So intercept of 12 here and slope of -1. We have the marginal revenue curve, 12 minus 2Q. So it has the same intercept as the demand curve, but then slopes twice as steep. And this is demand. This is marginal revenue. The change in or the increase in revenue as you produce slightly more. So it's decreasing, and it's decreasing more rapidly than demand. The reason being, when you're producing more, you're also driving down the price. So that's affecting your revenue. Two effects on revenue. You're producing more units. That's good for revenue. You're driving down the price of everything that you're producing. That's bad for revenue. Both of those are going to be affecting the marginal revenue. In the case where demand is linear, as here, the slope of the marginal revenue curve is twice as steep as demand. So that's sometimes used as a sort of a rule for memorization, if you wish. One can do that, but is there anything deep economic behind that? No. It's just that when we're looking at the linear demand curve, where we have something in intercept minus Q. We're multiplying that with Q, and we're differentiating. So we get Q squared. We're differentiating with respect to Q. We get minus 2Q. Okay, so that's just happens to be the case for linear demand curve. We have the marginal cost. So let's draw that as well. So 2Q, something like this, I guess. Obviously, I'm doing this totally by hand, so don't take a ruler out, but the general picture should be clear. Okay, so what's the optimal quantity here? What's the profit maximizing quantity? Well, it's given by this. We could calculate it. So what do we have? We have that collecting terms here. We have that 4Q equals 12 minus 2 minus 2, or that Q star equals 12 divided by 4 equals 3. So the profit maximizing quantity is 3. What's associated profit maximizing price? We could think that it would be here, but no. Remember, we have the demand curve, 12 minus Q. So what's Q? Well, it's 3. So plug that in here. So if 3 units are produced, what's demand? What's the price that's clearing this market? Well, it's 12 minus 3, or 9. So that's the price that's going to be resulting if 3 units are brought out into this market. Okay. So equilibrium, or no, profit maximizing quantity, associated profit maximizing price. Why is this a point? Well, essentially, if we're producing less, the monopolist is producing less than 3 units, it's losing out by not producing more. Essentially, we have, say, point like 2.5. We have marginal revenue that's greater than marginal cost. So if the firm was to produce a little bit more, the increase in revenue would be greater than the increase in cost. Go ahead, do it. Okay, and be increasing revenue. Whereas out here, if you're producing a bit more than 3, the increase in cost given by the marginal cost curve is going to be greater than the increase in revenue from that increasing quantity. That's not good for overall revenue, or overall profits, rather. If you're doing something that's hurting more than it's benefiting you. Okay, and the sweet spot is where marginal revenue equals marginal cost. Okay, what are profits in this case? We could, calculate them by taking the 3 and the 9 and plugging into the profit function, calculating profits. But for a number of applications, illustrations, we often want to be able to draw to illustrate the profit in the figure here. So to do that, let's work on a little trick, or not trick, but something that helps us for illustration. We also clean up a bit here, so don't want things to get too messy. Okay, so we have profits equal to, I guess in the general case, we could write that profits is equal to price minus, or price times quantity minus cost. Okay. If we know where we're going, we can multiply by Q and divide by Q here. So that's like multiplying and dividing by, or multiplying by 1, right? Q over Q is 1. We can do that. Why did we do this? Well, we can note that this is the average total cost. It's total cost divided by the number of units. Okay. Also know that we have Q here. So if we break out Q, you see that we can write price as, or profits as price minus average total cost, like this, times Q. Okay. So in this case, we know price, 9. We know Q, 3. What are average total cost? Well, that's C of Q over Q. And in the case where Q is 3, so that's 3 plus Q squared, which means 3 squared, over 3, the quantity. Okay. So that's 9 plus 3. It's 12 over 3, which is equal to 4. Okay. So something like here. So there's an average total cost curve. I can draw that. Here we're just doing it on freehand. But essentially there's going to be yeah, I don't know exactly where we're drawing. This might be a bit wrong. The important thing is, for our purposes, is that two things. It will go through the marginal cost curve. The marginal cost curve will cut the average total cost curve as its lowest point. We covered that in previous chapters. For our purposes, the most important point, though, is that we have one point on this curve that we've calculated, 4, at the quantity of 3. So we can express profits as, in this case, price, 9, minus average total cost, 4, times quantity, 3. So that's 5 times 3, or that's 15. And we can draw that in this figure. Okay, so that's this area. That's profit for the monopolist in this case. Okay, so nothing mysterious. How many units are you producing? 3 units. How much do you make on average? Well, that's the difference between price and the average cost. And that average total cost will differ depending on where we evaluate it. Okay, so that's yeah, that's it for monopoly.